Hmm. Okay, it looks like it's working now. So I have to log out. Hello, hello, hello. How's everybody doing? I'm in San Antonio, Texas. It's 9:40 Central Time in Texas, San Antonio. I see three viewers. Where y'all viewing from? If y'all can put where you're viewing from, that's always interesting. Flavio Ramos. Hi, Flavio Ramos. Where you from? Wow, Brazil. Wow. How you doing? Welcome. Unsearchable thing. Huntsville, Alabama. Hey, welcome. Oh, by the way, the Alabama football team won in spite of the quarterback being injured. They got a pretty good football team. So, are y'all power engineers or students or practicing engineers? Yeah, I hope they're still undefeated, I believe. Oh, Brazil. Oh, Brazil's a powerhouse. Six-time world champion cup. Ah, yep. Unsearchable team. Electrical engineer. What kind of electrical do you do? Unsearchable thing. What branch of electronics or electrical? How about you, Ramos? Flavio Ramos. Oh, cool. I'm an electrical engineer, undergrad student with emphasis on electronic, both microelectronic. Actually, that gives you, if you study microelectronics, it makes you better in power electronics because you'll have an understanding of how the analog circuit chips work. So that's a pretty pretty big combination, Flavio. I congratulate you on that. That's really really good. If you do the microelectronics, especially if you do like VLSI and understand the CMOS, and that really really helps you. It gives you a much better understanding. So congrats. Okay. So, so engineering. So how much more do you have to go to graduate? Are you the what year are you in? And also guidance, navigation, control, electronics. Oh, cool. Yeah, as a matter of fact, that's my background. I actually got my master's in analog IC design. I used to work at Sony Semiconductor, and I wanted to design chips for Sony. I used to work in a fab, and I wanted to, like I said, design. So I started taking classes in analog design. But Sony shut down, and they laid off everybody, and I had to find a uh, power engineering job. So it helps a lot. Flavio, 1 year to go. Congrats, 2023. Uh, I have a daughter, 21, 22. She'll be graduating next year too, so it's good. Hi, Vivek. Good morning. Were you writing, Vivek? Major master's was control theory, minor and middle set. Ah, unsearchable thing. Ah, see, oh, you got a good background. VLSI design. Yes. And then you have the powerful combination of control theory, which is very good. Oh, I'm in San Antonio, Texas. San Antonio, Texas, and it's nighttime. It's 9:46 at night here. So yeah, I decided to see what's going on and chat for a little bit. See if you have any questions on electronics or power electronics stuff that sometimes that I do get emails through emails question, and sometimes I'm kind of uh, swamped with a lot of work, and I don't get to answer all of my uh, emails. Yeah, I don't think you'll have problems if you know analog and power electronics. I think the market out there. Uh, uh, I know that we're in a recession, but there, at least in the U.S., it's officially in a recession. But I think there's a lot of demand for engineers. So I think you should be able to land jobs. I know when back in 2004, uh, that's when Sony shut down, and it was very hard to find jobs. So I don't see that condition right now. Things are a little bit better than it was in 2004. That's when I went through, or at least in the U.S., there were quite a bit of layoffs and so forth. So I think you'll be able to find a job, and and if you can, see if you can get an internship. Okay, so the question is, do you think chip design is easier to find, easier field to earn a living than compared to power, energy, and power electronics? I think you probably find more jobs in the power electronics, to be honest. If you're going to do VLSI, you probably have to work with some of the big major companies. And I'm assuming that they allow remote access to their VLSI. And I think most companies use Cadence for their or Mentor Graphics, but I think for analog it's Cadence. I know that when my son took a class in VLSI design, and he would log in remote to his university, and he was able to do uh, uh, use Cadence remotely. But I think you can find more jobs as a power electronics. One way to find out is wherever you're at. Flavio, since you're in Brazil. I'm not here in the U.S. is I think Indeed. I don't know if they have Indeed, but they probably have an equivalent in Brazil. I would do a Google or a search for VLSI design, and then see how many jobs there is, and then do one for power electronics. I think you'll probably find power electronics more, many more of the numbers. Okay, Vivek. Hey, Vivek, where are you writing from? I'm interested. And he's asking. Okay, Vivek is asking snubbers used to cross flyback winding and across the switch. What's the difference? Okay. Well, if you use a RTD, or at least the way I do the snubbers on the primary, I connect them across the primary of the primary of the transformer, and I don't use RCD. I use an RC, and that really dissipates or damps very well, and the power is dissipated through the resistor. You can do a RCD as well, and I believe some of the power is returned back to your VCC. So I'm not sure if it makes it more efficient, but you may want to do a simulation on that. And I'll probably do a simulation to find out myself too. And then I've seen some snubbers across the MOSFET, and typically that would be to try to protect spikes. Usually, if you have like a leakage inductance in your flyback transformer, if you have a lot of leakage, you're gonna get a big spike. Okay, so typically, whatever the current is going through the primary, you gotta remember there's a leakage inductance. That leakage inductance is carrying the same current, and when you turn off the MOSFET, the energy that's in the leakage inductance, it has to go somewhere. So it goes back into the flyback, and it's to find the spike is supposed to be the current through the leakage inductor times the natural impedance, which is the square root of L divided by C, which is uh, the capacitance of the MOSFET. So that's how you kind of figure that out. I think I have a video on that on leakage, how to calculate the leakage, how much it rings. So you might want to look in my channel and see if you could find it. I kind of derived the equations, and hopefully I explained it well enough where you can understand it. Ah, yeah, Bob Peace. Yeah, he's a character. Yeah, I like to read a lot of his old articles. I believe he went to MIT. He's an MIT graduate, I believe, if I'm not mistaken. And another good one is, well, everybody knows, or you should know, Bob Weitler. He's the father of the op amp. And I don't know what university he went, but he was definitely a pioneer in the analog electronics. Ah, Pliskin. Yes, I bought the book too. Oh, and you have the signature? Oh my God. Damn. I envy you. Damn. To get a signature from Pop Weiss, please. Yeah. Luckily, uh, he was, how can I say, he lived long enough to, for YouTube and video. So there's quite a bit of video on him. and of course his is articles that he wrote for, I think, electronic design. I think, if not mistaken, maybe you guys would know. But I'm glad that he lived long enough to record. I wish Bob. Uh, uh, Man, I'm having a senior moment. Sorry. Oh, Bob Weiler. I I haven't seen any videos of him or any articles that he wrote. I wish he had lived long enough to have seen some video on him. It would have been nice to find out what his design philosophy and how his brain ticked. And Flavio says Weitweiler is from Colorado, Boulder. Wow, that's a good university. My son wanted to go there, Colorado, at Boulder. So yeah, they're real good. Oh, Vivek, ah, from India. Hey, greetings. I hope everybody's doing fine over there. I hope it 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 looks like we're over the COVID. I got it twice. I got COVID twice. The first one I posted when I got COVID, and but the second one really kicked my butt. And I was already vaccinated, and yeah, I had a hard time the second time. As a matter of fact, I ended up with pneumonia and was coughing up some blood. So luckily, I got a monoclonal infusion and was able to recover from the COVID. So I hope everybody's recovered and doing fine and doing good. Everyone in nature, may all your troubles be middle sized so you can find them. Ha! I think, yeah, Bob P was very funny, uh, very entertaining in his videos that, uh, that he recorded. I think a very unique character. That's what I like to read about and find out about analog designers. What makes them tick, or what how their mind works. That's always been a curiosity to me. Uh, what makes them tick, what how they think, and then I try to see, do I think that way or not? But anyway, yeah, I Flavio says asking if I recovered. Yeah, yes, I recovered. Uh, it did take some time. I had, well, the first time that I got COVID, I had what they call long haul COVID. So I had the symptoms for 5 months, and that was not fun. So there were days that you would feel good, and you say, "Okay, I'm recovered," and then the the symptoms would come back and hit me. So I I had trouble managing that psychologically. I was going a little crazy there. You know, actually got into a little bit of depression because I didn't know whether it was hard to see whether I was actually over the COVID symptoms. But I think after the 6 month, I felt better. And this was toward the end of last year. I think I got it in March of last year, and then this year in February, I got it. Oh, and I got it from my wife. My wife is a teacher, elementary teacher, and she got it from her students. She got sick, and of course, I caught it from her, and we're both sick. And then daughter, my oldest daughter, got it. So yeah, that was a downer, but we got over it. Okay. Yeah, I actually on the 6th day, uh, I got the monoclonal infusion, and that really worked. After I got the monoclonal infusion, which is through an IV, So 24 hours, I felt much better, but the virus had already damaged my lungs, and they were filling up with fluid, and I was coughing blood out with phlegm and stuff, and I had a hard time getting up, walking from my bed to the bathroom and back. I would be gasping for air, so that was scary. So if I don't get had I not gotten the monoclonal, I don't know if I would have recovered. But thank God, uh, the doctor that I went scheduled me for monoclonal, and I was able to get the infusion. So yeah, I feel better. Hi Sal. Hey Sal, how you doing? I'm still trying to figure out whether I can do that. I'm gonna see if I can copy that worst case analysis book for you. I know that the company is no longer in the field, so I might see if I can copy that. It's just that it's so many pages. It's probably close to well over 500 pages, and it's kind of hard to, and it's front and back. That's what makes it difficult to copy and scan. So so I hope you're doing good, Sal. Let's get. Oh, After Effects. I don't know if there's any After Effects. Uh, I'm 61 years old, and when you are 60 in your 60s and chunky, fat, uh, everything hurts. Your knees hurt, hips. So you young guys, stay in shape, exercise. Don't do what I did. Don't overeat. Anyway, so no, actually, uh, trying to stay fit. I'm gonna see if I can start walking a little bit, maybe get a little healthier. Uh, by no means, I'm not as healthy as I should be, but I used to be much heavier. I was up to 292 pounds. I'm 265 right now, so I need to. I would like to get to about 240 if I can. Ah, you know what, Carlos? That does help. I do use the CBD. Yes, that actually does help. I use it on my knees, and I can definitely feel the relief. That's absolutely true. And then the other thing that I should go is do some stretching exercise. You don't As you get older, things tighten up. I guess that's the bad thing about analog design or power design. We tend to be sedentary. We sit in a computer all day simulating, designing. We don't do the physical work. So that's the drawback of being a designer. But if you guys are young and you like to play soccer, man, by all means, after you get off of work, go go play and do something. So yeah, definitely. If you can keep active and stay active, that's long terms. That'd be better for you. Yeah, 10-minute walk would probably help me. Absolutely. Yeah, that would definitely. Yeah, what I'm gonna do is I'm gonna do the CBD on my knees and then do some walking. That's At my age, that's uh, that's all you can do. You walk. When I was young, I used to play a lot of basketball in my 20s. Throughout my 20s and early 30s, I played basketball and volleyball, and I actually was pretty fit. I weighed 155 pounds, and I was very fit. So, but it's a lot of wear and tear. Adrian, hi, how you doing? Welcome. Okay. Do y'all have any questions on power electronics or career, or I can answer any questions that I'll try to. Do I have a question? Mostly. Okay, Flavia says why most APEC top presenters focus on DC to DC converters. I don't find many people looking for DC to AC. That's a good question. I'm not sure. I do DC to DC converters, and it, it's in my field. It's kind of obvious. I do space. So in space, the spacecraft gets uh, their power from solar cells, right? They have the spaceship has the solar cells, and it's a DC voltage, and I believe they have batteries too to charge the batteries and maintain them, and then from there the bus is going to be about 28 volts. So from there we regulate either through typically we'll use a forward converter and we'll regulate down to 12 volts or 3 volts. And if you have a FPGA 3.3 down to 1.5. So we're at least in my field and space industry, it's DC to DC converters. Uh, I'm not too familiar with inverters, so I really can't comment too much about that. But I know that we did have an engineer that came from that side. He designed inverters and he was able to make the transitions here. Ah, okay. Unsearchable thing says same in the military. They have the input of 28 input volts. Yeah, I think that's where space kind of copies because we use a lot of the mill standard documents that are out there, and like for EMC, I think it's the mill standard 461. I forgot which is the latest D or F or something like that. So yeah, we follow the military standard quite closely. Okay, on ferrite beads, yes, we use ferrite beads as well. Uh, for example, if we have 12 volts on a power supply, we may have 12 volts, and that 12 volts can split into two sub circuits. So one circuit could be, uh, let's say, regular electronics, but then there might be another sub circuit or sub circuit that is like RF. Okay, so the RF typically you need more filtering, and in the past we have used on the 12 volts that goes to the RF, we'll use a ferrite bead as well, and that helps, at least from my observation. If you have a high frequency, the switching frequency, let's say your converter is running at 200 kilohertz, you'll see the switching, the little spike. So remember, the if you have a forward converter, the ripple looks triangular like that, and then where the rip, maybe I should write it down. Maybe I should do this. Ah, let's see, do I have a pin? Okay. Yeah, so you have your regular, so you have your ripple like this, but then when you put your scope probe, And especially if you have your scope rope is long, you'll get these little spikes. Okay, that's mostly common mode, and they're high frequency. So if you use a ferrite bead, these these get attenuated somewhat. So it helps in the ripple, but you have to be careful. Make sure that they're properly damped. I know that Steve Sandler uh, uh, always throws caution, or he always says for us to be uh, double check. Make sure that you don't have a high Q uh, due to the filter. Gregory, hi Gregory. Ah, okay. So Greg says that Mill Standard 74 has 28 volts as a power source for aircraft, and Mill Standard 1275 has 28 volts for ground equipment. Is what we use for power. Wow, cool. I do know. I did get a chance to work on a power supply for an aircraft, and their specifications or requirements are really, really tough. I remember, without giving too much data, I know that on one of the requirements, uh, the the power supply has to hold up its voltage if your input goes below us down to, I think, down to 8 volts. It has to hold, and for that you have to have enough a lot of capacitors at the input. So uh, aircraft power supply designers, that's really tough. So, they- but I did get a chance to work on one of the. Okay, filter. Okay, great. Oh, okay, Plinkin. So you must be. I worked with you then. I'm trying to remember. What is your name, Pliskin? I know that you were working in the second floor. I'm trying to remember your name. Darn. Help me out, Pliskin. What's your name? Ernesto. Ah, yeah. Then you go to up to Austin. I think you went to Austin. Yeah, John Stone. Cosmic prayer beads. Yes. We use them, but we make sure that they work and we don't have any gotchas. Absolutely. So, what is the fusion microgrid from AC to DC? Okay. Okay. I'm sorry, sir. I haven't done AC to DC, so I don't have the expertise to answer that question. My expertise is DC to DC. But if I was to think about it, I can probably figure it out. Hi, Jesse. Yes, my sister is Beatrice Colunga. Yes, she's my sister. She's a nurse. Yes. I also have a sister named that's a nurse too, Linda Gomez Bolaños, and then I have a brother. He's in Houston. His name is Arturo Bolaños, and he's a QA quality engineer He recently had a stroke, so now he's uh, disabled. So, but he's not. I mean, he's doing fine, but he survived the stroke. But he's doing, he's recovering, and he's doing real good. So we're trying to help him out. As a matter of fact, I'm gonna go visit him in Houston in about 2 weeks. So yeah, wow, Jesse Turner, wow, small world, interesting. What do you do, Jesse? What brought you to the channel, Jesse Turner? Oh, okay. Paul Gregory Paul says the holdup requirements can definitely be difficult to deal with for some of those aircraft systems. Yes, that was very difficult. So the way I was trying to get it, if I remember, the voltage, the standard bus, I think was 28, and the power supply, and in this design, I'm not going to say which plane it is because I might not be allowed, but I can say that it's for a jet fighter. Okay, and uh, and one of the requirements was it had to operate all the way down with an input bus of 8 volts, and they gave us a certain time that it had to hold up, and that was very tough. So, and the way we got around to it is we had to use a typically when you use a converter, whether it's a flyback or a forward converter, uh, we try to limit it to 50%. On a flyback, you can go up to 99% duty cycle. So I think we ended up doing a forward, no, no, a flyback. I don't remember right now. It's been quite some time, but yeah, aircraft is very, very, very tough. Ah, Pliskin, Ernesto, you're working for Emerson up in Round Rock. That's, I think, north of Austin. Wow, I'm glad that you're doing that. Jesse, electrical engineer, I'm getting into mechanical and aerospace engineering in April. Are you, Jesse, are you going to UTSA? I'm assuming you're at UTSA. Either UTSA or St. Mary's. Those are the two universities here in town. UTSA. Okay. That's good. That's where I graduated. I went to UTSA. Huddy N. Okay. How you doing, Huddy? I think I've interfaced with you before. I wish you could expand your to see. Selecting. Well, it depends what converter. No low condition. Okay. Well, no. On a forward, uh, you're always operating in continuous uh, current mode, and but you can't. You have to have a load if you're not using synchronous. If you use synchronous rectification, then you can operate with no load. Otherwise, you'll have to put a little bit of a load to keep it in the continuous conduction mode. I know it's a waste of power, but sometimes if you're not if you you cannot do synchronous rectification. You're just using diodes, then you have to you have to use a little bit of a dummy load. It will waste power, but you know unless unless you go with synchronous rectification, then that would be the way to go for no load. Okay. Ernesto, what are you doing there in up in Round Rock? Are you doing what you're doing at Southwest Research? Okay, Hadi. Isolated converter. Yeah, I'm sorry, Hadi. Yeah, isolated converter would be like a flyback or a forward converter. So a forward converter, uh, you can do a synchronous, and you should be able to go with no load condition. I think you can also do synchronous on flyback, I believe, but I'm not sure if you can do no load with synchronous flyback. So I would have to find out. That's a good question, Hadi. Good question, Hadi. You got me interested to see if you can operate a flyback synchronous rectification with no load. I'm gonna find out. I'm gonna simulate it. Okay. Well, it looks like well, there's a mix of okay. So Plinskin, uh, I work with Plinskin, or at least I met him at Southwest Research. He was working on the second floor of the building that I work, and he works with the space instrument, I believe. He would test them, and that's where I met him. And I believe he's from Mexico. I'm from Mexico, so I was born in Nuevo Laredo, Mexico. I'm not sure where specifically Bliskin or Ernesto is from, but I know he's from Mexico. Nope, I'm from Centennial. I thought you were born in Mexico. Okay, so I'm the only Mexicano here. Then, oh, he's Hispanic, but he's got, I believe he had green eyes. Huh. Yeah, but now I'm a U.S. citizen. So, as a matter of fact, I was just looking at my some documents, and I found my U.S. naturalization paper. It looks like I got my citizenship in 1991, which is what 32 years ago or something like that. So, okay, Paul. Good night. You take care. Okay. Ariane has a good question. Yeah, there's some FRA Bodhi plots that the phase crosses zero. Is that right? Yeah, it crosses zero, but the gain is still high, and then they'll go up again above the zero, and then the gain. In other words, let me draw it. Okay. 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 So the gain will look something like this, and then the phase will drop some. Let's see. So the phase will drop below zero, but then come up and then drop after the phase. No, after the gain crosses zero. Okay. So believe it or not, from my understanding, this is from Dr. Ray Ridley. that that's stable. At least that's what I recall. And and what's important is uh, the where the phase crosses after the gain goes below zero. So at least that's what I remember reading. You might want to go to Ray Ridley's website. I believe he covers that in there. So in this situation, it's stable, and the margin is it's actually here. It would be that's the one that you want to measure. These don't count, and the reason is because you have a lot of gain, and because you have a lot of gain, uh, it doesn't get stuck. It doesn't start oscillating. At least that's my understanding. So anyway, but don't take my word for it. Verify what I mentioned. I know that it's in Dr. Ray Ridley's website. There's an article that he wrote there, and he covers that. Okay, I should get our magnetic designer is a guy named uh, Dennis Dennis Guerrero, and he's our expert magnetic designer. Good. He's gonna check Dr. Ridley's content out. Yeah, so it should be. Uh, I well here's let me see. Planers are pretty neat. Let me see. Hang on, guys. I think I have a planer here. Oh, actually, if y'all work with planers, here's some samples of some transformers that I've wound. Okay. Okay. One of the things that really is very good in, especially in these classes, if y'all have an opportunity, if you get a chance to enroll in Ray Ridley's class, I highly recommend it. And the reason is because you get a chance to wind your magnetics. So I took his class, I think, in 2007. So he's pretty, uh, yeah, it's been some time ago. But in his class, I believe you did a forward converter. You wind the output inductor and also the transformer. So here's some. I believe this is EDF or E. Let me see. It's EFD 25, I believe. So these are for a forward converter that I'm trying to design. That's a 25, EFD 25, and I think this is a EDF uh, 30. So you learn a lot if you wind your transformers. So this and these are kind of like equivalent. And if you notice, using multiple windings. So this is a RM cord. Now the nice ones is if you can get one of these. These are planar. Okay, so these are from Coilcraft. These are really nice. So now, as a practicing engineer, if you email, or actually you can buy, you can get samples of from Coilcraft. So if you have a project, I think they allow you they'll to get three three of these samples. So if you have, I recommend trying some of these. And basically, it's a printed circuit board, and the printed circuit boards are the ones that have the windings. Uh, I'm not sure what the material is. I wish they would tell you the material, and they would give you more data on that. But you certainly can design your own. Dennis is our resident designer, so he's really good at designing these things. Okay. Oh, okay. So he says about the high frequencies. Okay, the material, the type of the material. That's one of the things that Dennis always tells me. Uh, De- Dennis tells me that since you're switching a square wave, in which is true, a square wave is composed of harmonics. So you're gonna have the first, the third, the fifth, and so forth. So you want to be sure that your magnetics, the frequency that it operates, that at least I would say maybe 5 times your switching frequency. That way, uh, you're able to pass all of that harmonics and so forth. In other words, you'll end up with a nice square wave. Okay, unless you're doing a resonant converter, then the bandwidth may might not have to go so high. But anyway, that's what Dennis tells me. Make sure that your material can handle the frequency. Okay, so questions. Okay, is there any other questions? If not, oh, one question that I have for you guys is, I know that Sal, one of the guys, emailed me. One of the questions that I would have is, what subjects would you guys want me to cover or do a video on? I know that uh, the WCA is one of the subjects, worst case analysis. Is that something that other people would be interested? Uh, Recently, I did a worst case analysis. Okay, yeah, I'll get back to Vic. Uh, Most of the time, I do worst case analysis. Okay, let okay, Vic and Pleskin has good questions on that. Let Let me finish my thought right here. Uh, okay, when I do worst case analysis, I use TopSpice as my simulator, and I have a methodology. And I think I have an introductory video on worst case analysis. But there is a new uh, software. It's been around for a long time. It's actually Microcap 12. Now it's free. You can download it. It used to cost $3,500. Now the guy uh, made it free to the engineering community. And what I found on the last version that he put out, he did a real nice worst case analysis feature. So I'm gonna do a video, or at least I'm thinking of doing a video using that software because it makes uh, the execution of the worst case analysis much easier compared to TopSpice. So what I'm thinking of doing is showing the way I do it with TopSpice, and it's a little laborious, and then I'll show how easy it is to do it on Microcap 12. So that's one video that I was thinking of doing. Okay, so now I'm going to ask him, is there any limit to how much power particular? Yes, you have to do the AP. You have to the cross area product. Yeah, So there's an application note by TI. It's an old application, and they have the equations in there. So uh, you put in your power and the frequency and so forth, and you calculate the area product. I think it's the window, the area of the window, bobbin window times the area of the core, I believe. So that will kind of give you estimate of how big your core has for specific uh, uh, power in core. If you guys are interested, email me. I have two Excel uh, spreadsheets. One is for flyback, and the other one is for forward converter. And it's kind of like a demo. But if you email me for those two spreadsheets, I can send you those. And on that one, on those spreadsheets, you can put your design parameters that you want, and then it shows a bunch of cores. And if the core is able to handle the power, it turns green. So any cores in the database that turns green, that means that you can use that core. And then you just type in the name of the core, and it updates and it gives you design. So it's a spreadsheet that I use for design. So email me at my email, rbola35618 at AOL, and I'll send you the forward uh, transformer design and the flyback converter design. So that should help you. Okay, as far as the frequency is concerned, okay, here in I know that they've been going to higher and higher frequencies, but in the space community, uh, we're pretty much from 100 kilohertz to 200 kilohertz in that area, and most of the power supplies that we design are 100 kilohertz. Why we're limited on the parts that we can select. Uh, the power FETs have to be radiation tolerant, and we used to get them from uh, International Rectifier, which is now Infineon. So those are the ones that we were constrained to use. Okay, because if you use a regular MOSFET, they don't work once they're radiated. So having said that, those FETs tend to have high uh, gate to source capacitance. VGS is high. So the higher the capacitance, the more switching losses you're going to have. So as you increase your switching frequency, then you get a whammy. You get a hit on switching losses. So you're going to have to do calculations or simulations to see uh, whether your efficiency suffers or not. And typically, like in a forward converter, we don't hit the 90s%. I know there's a bunch of companies that will and and that they're getting like 90% or low 90s. Uh, Typically, we'll get about 80 to 83 in that area, and that's because we built a lot of redundancy in our circuits and so forth. And that's the efficiency we get. But if you use commercial parts and you use GaN FETs, that's something that I probably will be. Actually, I've been using GaN FETs for the pulsar, and we might transition into GaN FETs. Okay, with GaN FETs, the characteristics that I've seen is they have extremely low CGS. The capacitance from gate to source is very low. Uh, I have used GaN systems. As a matter of fact, I thought I had some here. Uh, yeah, here's their GaN systems. Okay, the number is GS56. Man, I really can't see. Okay, so this is rated at 650 volts, and but they do this one doesn't have a low RDS. The RDS is about 200 milliohm, but I know that there's higher power ones with much lower RDS on. So if you have a low RDS on, then your conduction losses are going to be low, and because the capacitance are very very low, your switching losses will be low. So regarding GaN FETs, or if you're going to use GaN FETs, yes, you can go up in frequency. So yeah, that's something that we haven't done in the space community. In the space community, we're very into heritage. In other words, the customer or NASA or the European Space Agency, they want to make sure that their power supply that we're going to hire design has some kind of heritage. What does that mean? It means that design has already flown in previous flights, and since it has already flown in previous flights, then it's already been it's a proven design. So we basically use the same features or the same design. Okay, Adrian. Yes, a lecture on zero volt crossing. Yes. Okay, I'll do that. Hi, Don Barnes. How you doing? Don Barnes is a very experienced engineer. He works with us. He says that high frequency support parasitic. Yep, he's right. Yep, parasitics. They play a big uh, problem sometimes. So they can be problematic. So yeah, at higher frequency. So if you stay at the lower frequency, it doesn't affect you as much. But as you go higher and higher, uh, okay, here's something interesting. Don Barnes will know about this. Okay, okay. Uh, this is this is a coil to a RF oscillator, and this oscillator is going to be oscillating at about 2 megahertz, and it's and believe it or not, there's an inductor here, and there's a shield here, so there's straight capacitance between the coil and this shield. So you have to take that into account as well. So so I have it here at home, and I'm measuring, taking measurements, trying to figure out how to build this. So I'm trying to make this and shrink it into a smaller fit form. So that's been challenging, but we I do have already a design that might work. So working on that. So, oh, the email. It's rbola35618 at AOL. So rbola is RBOLA35618. I'll put it um, on the down below, and I'll send you the my spreadsheet for the flyback and for the forward converter. So, like I said, you you type in your parameters, your input voltage, your frequency, your duty cycle, and the output voltages and the current, and then this will tell you which cores you can use. And then once you select the cores, then once you put the the Teslas or the B field that you're going to be operating, and you want to keep below zero point 0.3 Teslas, below that, because at zero point 0.3 you start saturating. So if you put in, uh, let's say use the Pressman book. It says to use 1600 Gauss or 0.16 Teslas. Then it'll calculate how many turns. So then you can set the turns in the primary, and then it suggests what the secondaries are. So send me an email, and I'll send you those files, and I'll send you like a an instruction. I only have the instruction for the forward converter, but the flyback should be very similar. So once you know how to do the forward, then you should be able to use both sheets. Okay, I'm coming up at 1 hour. I'm gonna call it quits here, and I'll probably do another maybe in a couple of weeks, maybe next month. I'll do another one of these. In the meantime, I know that I'll probably be doing one on worst case analysis because it's been requested. Uh, I think it's a neat software, Microcap 12. It's got a real nice feature where you can do those worst case analysis. And yes, and Sal, I'm going to be doing the. I'm going to see if I can get a copy of that manual on worst case analysis. I'm surprised. There's not that much material on worst case analysis, and I haven't seen any videos. The WCA expert or experts or AEI, Analytical Engineering, I believe, incorporated, and the president or CEO is Charles Himowitz, and I've used them for one of the projects that I work on. They're very good. So I'm pretty sure once I do the video and post on LinkedIn, he's gonna chime in because he's a really good expert. So, but and frankly, WCA is very complicated. Uh, Building your parts database is takes a long time. So I'm gonna see if I can tackle that, and that'll probably be maybe 2 or 3 videos. So hopefully you'll find that useful for you guys. Okay, guys, I'm gonna thank you for watching. Appreciate your comments and participation. Appreciate it. See you next time, probably in a couple of weeks. And may you all remain healthy, and may your simulations always converge. Those with simulators know what I'm talking about. Okay, good night.